Maria is the next president of the International Federation for Automatic Control for the next training. So we are really pleased to receive her with this talk. And I invite Bing to introduce formally Professor Maria.
Oh, thank you, Tiago. It's my great pleasure to introduce Professor Maria Prandini. So she's currently a full professor of automatic control at Polytechnic di Milano, and she has made many contributions to the community through her research on stochastic hybrid systems, distributed and data-driven optimization, and federated learning in multi-agent systems, with applications to transportation and energy system. As many of you know, she has made significant contribution to our community by serving many leadership roles. As Tiago just mentioned, she's IFAC president-elect, and in the past, she served as the vice president for both IFAC and IEEE Control System Society. She was elected for IEEE Fellow in 2020 and received the IEEE CSS Distinguished Member Award in 2018. So without further delay, Maria, the floor is yours.
Thank you very much for the nice introduction and for the kind invitation. It's a pleasure for me to be here and share with you some of the results that together with my colleagues we develop on database multi-agent optimization. So the problem here that we address is that of decision making when multiple agents are involved and they are cooperative. They need to cooperate because they interact, and the interaction is due to the fact that they need to reach some agreement on a common decision, or they share a resource which is limited. We consider a problem that can be formulated in terms of an optimization program, which has a partially coupled structure through decision, as I was mentioning before, or through constraint coupling. And the key feature that is addressed here in my presentation is the case in which the agents operate in an environment which is affected by uncertainty. This uncertainty influences the local constraints of the agents, and it's known only through data. And these data, they are private, a finite number. We'd like to preserve this privacy of data, so the data are not shared among the agents that's using distributed optimization scheme, while guaranteeing generalization property of the decision that is taken by relying on this data. So just as an example, to show that these problems are actually encountered in a variety of applications in energy, transportation, robotics, and wireless communication, consider the case in which you have a district of buildings, and these buildings are equipped each one with a chiller plant. So this chiller plant converts electrical energy in cooling energy and serves its own building, but it could also provide some cooling energy to a thermal storage device which is shared among the buildings. And through this shared storage device, which is a limited resource, you can get an advantage in terms of minimization of the cost of electrical energy consumption for cooling the overall district over one day time horizon, while guaranteeing comfort condition in terms of temperature and humidity of the different control zone temperature in each building. So there are some ingredients of the problem. I'm describing them at high level, but basically each chiller plant is characterized by a coefficient of performance, which is the ratio between the cooling energy that is produced by the chiller and its electrical energy consumption. You can have plants with different capacity, medium, small, and large here, depending on how much cooling energy they can produce. The large one, yellow, larger amount than the medium and the small size. And in order to be cost effective, the chiller plant should operate at the peak of the curve so that they make the best use of electrical energy. But depending on the request of each single building, if they would operate separately without any thermal storage, you'd get a certain cost of the energy, while the advantage of sharing cooling energy produced by the different chiller plant is that possibly you can operate the large one at its highest efficiency point by serving also the needs of neighboring building. This is the idea. In order to take your decision on how to handle the storage system optimally to get the minimum of the cost, of energy cost, you need to characterize the cooling energy request by each building, and this is determined by external signals related to the radiation through windows, the people occupancy, and also internal energy contribution like internal lighting, but also of the characteristic of the buildings in terms of thermal dynamic and zone inertia. As for the thermal storage, you can describe it simply as a sort of integrator with a coefficient alpha smaller than 1 that accounts for energy losses, which basically receives as input the sum of all energy exchanges energy exchanges by all buildings, which are positive or negative depending if they are discharging the storage, taking energy from the storage, or charging it. This is a simple dynamic. And overall, the decision-making problem formulation consists in minimizing the sum of the cost of the chiller electrical energy consumption, as I was mentioning before, subject to a number of constraints. In particular, you have the storage dynamic and its limits in terms of capacity, and locally to each building and chiller pair, you have a balance of cooling energy. So the one that is requested to the chiller plant is the difference between the need of a building to have certain comfort condition minus the energy that it gets from the storage, and plus actuation limits and comfort constraints on the temperature that you realize in the control zone. How can you translate this in an optimization problem? Well, you need to decide the decision vector, so the vector of your decision variable. And you can think about having a decision vector in which all building and chiller pairs, each one represents an agent, should agree upon by putting together all the storage used by all agents. And it's not difficult to imagine. I didn't put the equation here because it's just to show that indeed this problem show up in energy context. You can formulate your optimization problem as a decision coupled problem given the definition of X, storage used by all agents. So you minimize the sum of energy cost per chiller subject to constraints that are local to each building and chiller pair, and that relates to the actuation capability of the chiller, the comfort constraints, plus the storage limits. Or alternatively, given the same problem, you can define your decision variables as local to each agent. So the xi variable would be the storage used along the day of a single building chiller pair I. And then rephrase the problem as a constraint coupled problem. Each agent has its own cost, electrical energy cost, that depends on its own usage of the storage, is subject to local constraints related to comfort and chiller constraints. And then the decisions are coupled through the usage of the storage. So these are different formulations for the same energy management problem. And this kind of constraint coupled and decision coupled problem are the ones that we are going to refer to in this presentation. They are encountered in different frameworks, and this is just one example. In order to formally address the problem and provide the robustness and embed uncertainty and then provide the robustness guarantees to the resulting problem, I need the unifying formulation. And indeed, both the decision coupled and constraint coupled optimization problem can be reduced to the same unifying form, which is written in these slides. So you have a decision X, which belong to a capital X set. You minimize with respect to this decision variable a function f of x subject to constraints that are local to each agent. So you need x to belong to the intersection of these constraints that are specific to each agent I. How can we fit the decision coupled structure into this formulation? It's pretty easy because in the case of a decision coupled problem, you have that x, it's the decision coupling variable. The capital X set is simply Rn. F is the sum of a local objective function of each agent, and then you are done. It's a little bit more involved to recover this formulation from the constraint coupled formulation. You need but it's relatively simple. You just need to put together all the local decision variable xi in a unique vector to define this capital X set as the one dictated by the coupling constraint, and then extend the local constraints by accounting for the other decision variable of the other agents, which are left free if you consider agent I, and then still define f as the sum of a local cost. So constraint coupled and decision coupled problem can be studied by referring to this unifying formulation. I wish I convinced you about that. So from now on, till when we are going to talk about distributed architecture for solving the optimization problem, I will refer to this unifying formulation. But one ingredient is missing. I told you we are interested in problems that involve cooperatively multiple agents that operate in an environment affected by uncertainty. And indeed, in our example, for instance, the building cooling energy requests are affected by uncertainty because they depend on the radiation of solar radiation through windows, people occupancy, external temperature, just to mention a few. And if you look, for example, at the characteristic of radiation, short wave, long wave radiation, it's really varying depending on the day. So the risk that you take by solving the optimization problem referring to a nominal disturbance is that your solution, which is supposedly optimal, won't be feasible in practice. Because when you apply it, you are encountering a different realization of the disturbances, and it might be that you don't meet, for example, the actuation constraints with your choice of a decision variable. So you need to robustify your decision against uncertainty. So what we are going to do next is indeed to describe this data-driven framework to account for uncertainty in a multi-agent optimization framework context. And the key feature of our data-driven framework are as follows. Data are finite and private resources. So each agent has its own finite amount of data and doesn't want to share it with the others. We want to provide a certificate of robustness so that our database decisions are guaranteed to be feasible with a certain a priori defined probability. And then you want to find the optimal solution of these data-driven problems in a distributed way so as to preserve privacy of local data. And so next, what we are going to do is first define our problem setup, then do this robustness assessment with analysis of the probabilistic robustness guarantees in terms of scalability, property, in the number of agents, and then discuss a bit about resolution schemes. So this algorithmic architecture that allow to preserve privacy of data by operating in a distributed manner. So as for the problem setup, remember we had a unifying formulation where we minimize with respect to a decision variable belonging to a set, our function f of x subject to constraints, but these constraints, local constraints, are affected by uncertainty. So I'm modeling representing uncertainty through this delta in red parameter that collects all sources of uncertainty. That would mean in my example, the solar radiations, the outside temperature, the occupancy in terms of people, the lighting, and whatever. So this uncertainty parameter take a value in some capital delta set. And if I solve this problem knowing this capital delta set, I would robustify my solution with respect to all possible realizations of the uncertainty. But I told you that uncertainty is known just from data. So how can I manage? So first of all, I have to put some embed my problem in a stochastic setting so as to be able to provide probabilistic guarantees. In particular here, I'm assuming that this delta, this uncertainty, comes from some underlying probability space characterized by a probability measure over a set capital delta, which can be possibly a continuous set. Unfortunately, these capital P and delta are not known. This is typically the case. I'm assuming that uncertainty is known directly through samples, which are assumed to be independent and identically distributed, so distributed over delta according to this unknown P, and I'm calling these data scenarios. So the natural formulation coming from the robust formulation of the problem, the natural one based on data, is as follows. I'm replacing the capital delta set with the variable data set capital S of scenarios. And I'm then formulating a randomized optimization problem, which depends on data. The data that are, the instructions that are available of my uncertainty parameter. So although we are interested in the case in which agents have their own data set, I'm starting from the case, not so much realistic, but useful to understand the development, where agents have all data in common, they share the data, and they have the same data set capital S. And then I move into the case of interest, where agents have different private data set, a collection capital Si, with I equal to 1m as the number of agents. In this case, the data-based problem gets reformulated locally. Each agent is using its own scenarios to enforce constraints. There are some assumptions, structural assumptions on the problem under which we are able to develop our robustness guarantees. We need convexity. This is quite standard assumption also in distributed optimization, and is an assumption with which the control community is quite familiar, because we try every time to massage the problem in order to get convexity. Convexity is nice because of the property of optimization problem, the resulting one. So I'm assuming that the function f and the set x are convex, and then also the local constraint set are convex for every uncertainty instance, and then the problem has a solution. So non-emptiness interior of the intersection of all constraints and compactness, both in the common dataset case as well as in the private dataset case. So now let's get started regarding probabilistic feasibility robustness guarantees from the common dataset case. So we have a database program. Given this program, with appropriate tool, everything is convex, we can supposedly determine the optimal solution. But now our problem of interest was actually the robust one, where we had 100% guarantees with respect to uncertainty that our solution then would be feasible. And the natural question is the following one. Is the solution to a database program feasible for a robust program? And is it true for any multi-sample capital S? Because remember, the database program depends on the scenarios that we have available. So here is just to say that there might be different multi-sample capital S, and there might be a bad one for which feasibility of a robust program is not guaranteed. Indeed, the best we can opt for is to characterize robustness in probabilistic terms with a certain confidence, because we could be very unlucky and, for example, our set of multi-sample is all identical. And in that case, we don't expect to have robustness and generalization property of our solution. There is a result which is ready to be used also in this multi-agent framework from the scenario theory that have been developed starting from this work of Calafiori e Campi, published in Transactional Automatic Control in 2006. Maybe there was an earlier one in 2005, but that's the time where the scenario theory was developed. And scenario theory is a theory that addresses exactly our problem, characterized robustness of a data-based scenario program. So under the assumption that I made on IID sampling from the uncertainty, the following results hold true. Fix a confidence parameter beta in 0, 1, then we can state that with confidence larger or equal than 1 minus beta, the probability that the solution of the database program violate at least one of the local constraints of the agents is smaller or equal than a certain quantity. And this quantity, epsilon, the violation, which we would like to be as small as possible, depends on three quantity: the dimensionality of the problem, so the number of decision variable n, the cardinality of the data set, and the beta confidence parameter. So this formula is not so straightforward to be understood in terms of dependency, but if you use this upper bound, which is a bit conservative, but quite easier to grasp, you can see that confidence in some sense is cheap because it enters logarithmically. So you could push your result to all through almost deterministically by setting beta very small without losing much in terms of violation, epsilon. It's inversely proportional to the cardinality of a data set. I think it's intuitive that the larger is the data set, the more you have a representation of a real underlying uncertainty, your probability space. And so you decrease the epsilon violation. And it's linear in the number of decision variable, because the number of decision variable in this convex context, it's actually a bound of the complexity. What do I mean by complexity? The notion of complexity is related to the cardinality of a minimal support set. What's this minimal support set? It's the subset with minimal cardinality of constraints, such that if you solve your optimization problem just using these constraints, you are going to get the same result. So for example, here, let's consider the case in which the dimensionality of the problem is 2. So you have 2 scalar decision variable and you want to minimize x2. And these sets, which are convex, represent your constraints related to a scenario. So as you can see, X star here, it's the solution which stays inside each one of this convex set. You can remove all set except these two. And if you consider just these two, you're going to get the same solution. So this is the minimal support set. And its cardinality, which is denoted in the following as D, it's 2. If you have other extraction, another set, data set, it could happen that the cardinality D of a minimal support set would be smaller, equal to 1. But you can prove that if the problem is convex, this D dimensionality, which is the complexity of a problem, cannot be larger than the number of decision variable, which becomes an indicator of complexity, as I mentioned before. So let's go back now to our problem and address the case of a private data set. So you can still write your program, find a solution, and pose the same question. Is there any robustness guarantees generalization property of a solution that I found based on data, on private data set? And how this relate to our robust program P delta? And still, we can apply the same result of Calafiori and Campi, conditionally to all scenarios of all the other agents, integrating with respect to the realization of this scenario, and get a result which, however, it relates just to the single agent robustness, because now each agent has its own data set. And in particular, what we can state is that the probability that the decision taken violate the local constraints of agent I is smaller or equal than an epsilon violation parameter, which is computed based on the same formula, because it's the same result that we are using. But now here, in place of the cardinality of the set S that was shared in common, there is a cardinality of a set of a single agent, and it's beta I. So each agent could state the robustness of its own solution using this bound. But then if you are interested to a global multi-agent system robustness property, and then it's relatively easy because, as you know, probability satisfies this additivity property. So the probability of a union of events is upper bounded by the sum of the probability of its event. And using this property and this previous result, then I will point you to the reference where you find all the derivation, but I think it's quite intuitive. Then you can upper bound the probability that the database solution violate at least one of the local constraints of an agent is upper bounded by the sum of the previous violation. That holds true for each single agent. So apparently we are good because we found a solution to our needs of a robustness certificate. But this solution is actually not particularly good because it scaled badly with the number of agents, at the point that if a number of agents is very high, by summing up this epsilon, you get a number larger than 1. So you violate the probability 1. And why this bound scales linearly, approximately linear with the number of agents? Think about the case in which the cardinality of each local data set it's identical and equal to n, capital N, just to make a symbol. And you divide the confidence equally among all agents. Then this quantity epsilon given by this formula will be identical depending on m through this beta coefficient, but in a logarithmic way. The resulting sum of this quantity would be m times the epsilon bar, and due to the light dependence on epsilon bar logarithmic through m, it's basically scaling linearly. And here is the problem that I mentioned, that if you have many agents, then it's very likely that you get a number larger than 1, and so a violation with probability 1. So the question is that can we do better? And the answer is yes, we can do better by using some results of the scenario theory, which rely on an a posteriori evaluation of the complexity of the problem. So single agent robustness guarantees that we derived before are a priori, and they rely on an assessment of complexity, which is this n. But indeed, you can think about evaluating and assessing complexity by counting the cardinality of the minimal support set, and in particular, the contribution to this cardinality of each single agent. So here is an example. Let's say that we have 2 agents and still 2 decision variables, so n equal to 2. In green, I'm drawing the constraints, linear constraints for simplicity related to agents 1. Depending on the uncertainty instance of its own local data set, you get these 3 different, consider cardinality 3, the data set. And here the blue one are instead the one of agent 2. So now the solution, if I'm minimizing with respect to the vertical axis, it's supported by 1 constraint of agent 1 and 1 constraint of agent 2. So the local complexity is respectively 1 and 1. For another data set, collection of data sets, you could have a different configuration where the complexity local to agent 1 is 0 and the one of agent 2 is 2. So if you think about more than 2 agents, given that the complexity is in any case no larger than 2, you end up that many local complexity would be 0 because the overall sum must be 2. And then this is the advantage of using these a posteriori single agent robustness guarantees based on this weight and judge approach, a posteriori approach. You add that the probability of agent I to violate its own constraint when using the decision that is computed based on the data-based scenario approach. It's upper bounded by the same epsilon expression, but now the arguments are different. The first one in particular is not anymore n, but is this di evaluated based on the local data set, number of scenarios in the minimal support set belonging to Si. As I mentioned before, this is smaller than n, at most n, and for most agents, if n is small compared to m, it's going to be 0. So a little contribution of epsilon I. This comes at the price of rescaling the beta I coefficient, because here instead of beta I, you have beta I divided by n plus 1. But since, as we saw before, confidence enter logarithmically this expression, this is a low loss in terms of epsilon value. And it's for sure smaller and equal than using in place of the I, the upper bound, n on complexity, but also locally. So still by exploiting the subadditivity of a probability measure, you can, based on this result, assess the robustness for the multi-agent system. So the probability that the solution to the scenario program violate at least one of the local constraints of the agents. This is upper bounded by the sum of the epsilon I violation, which are computed based on the local complexity. Good, because this is something that doesn't scale anymore linearly with the number of agents. As I mentioned you before, this di for m large compared to n are going to be, many of them, 0. But still, this is an a posteriori result, because I need to evaluate the I based on the collection of data set. How can we turn this a posteriori result in an a priori statement and assessment of the robustness of the solution, which is based just on the cardinality of the local data set? Well, these questions amount to evaluating the worst case value for this summation. Here, for ease of notation, I remove the other 2 arguments. What is the worst one? So we could use the conservative bound, but this is going to lead to a value which, as in the a priori case, it scales badly, linearly with m. The observation is that the sum of the di is upper bounded by n, which is the complexity overall convex optimization problem. And this is the key to get an improved a priori bound. What you need to do, and all the derivation are contained in this chapter of the Encyclopedia of Systems and Control Engineering published by Elsevier. It's basically to solve an integer optimization problem. You can do it numerically, where you look at the worst case value of the sum of epsilon I as a function of a local complexity subject to this upper bound, n, the dimensionality of the problem. And then you can state your a priori result on the probability of violation of at least one of the local constraints of the agent in your multi-agent problem, and then assess as a consequence the robustness. So just a pictorial view of how this bound scale compared to the worst case bound and to the bound in the common dataset case. So as the number of agents grows, the bound in the common dataset case keeps constant. The one that we just derived grows, but not too badly with the number of agents, while the one based on the a priori scenario theory scales linearly, as I mentioned before. So get worse and worse as the number of agents grows. And already with 15 in this setup, it touches almost 1, which means that the generalization property of the solution is very poor, 0 generalization. So up to now, what I address are the 2 points of my outline, problem setup and robustness assessment. So now we need to enter a bit about talk a bit about resolution scheme. I will make it shorter because I see that we started a bit later and then I want to leave space for questions. So we have our database multi-agent decision coupled and constraint coupled optimization problem. I'm going back to the specific formulation. Why? Because now I want to suggest distributed optimization scheme that are effective in preserving privacy of the local information. So I need just a partially coupled structure to do it. So assume that the agents can perform computation and communicate over a network. Is there a chance of solving the database multi-agent decision coupled optimization property preserving privacy? And the answer is yes. You need first to simply view this problem as a standard multi-agent decision coupled program. And this is easy because it's a matter of just setting the intersection with respect to delta belonging to Si of Xi delta as the local constraints of agent I. So it's just a redefinition, and that's all. Because this is the standard structure of a decision-coupled multi-agent program for which multiple distributed resolution schemes have been proposed in the literature, most of them with convergence guarantees to the optimal solution. And these are the ones you need to use. So basically, you distribute your computation among agents. Each agent uses as local constraint set the one that is associated with its own data set. And then once the agents throughout the iterative distributed scheme converge to the solution, that solution inherits the probabilistic guarantees of robustness that I mentioned you before. So you could use your favorite one. And I'm here just going through one that we proposed a few years back, which is called probabilistic proximal distributed algorithm. So the idea here is that you have agents that can communicate with each other. Here is a ring structure of the agents, recalling my first example. And each agent, here the generic agent I, it's marked with green, is going to solve the local optimization problems, exploiting just its local information. So the data through its local data set, local constraint set x bar I, its local objective function, plus the terms that account for the other agents. Xi here, it's the copy of the X decision variable on which all agents need to reach consensus that is maintained by agent I. And the idea is that each agent compute its candidate solution, exchange information with the other. This Xi should converge to the same X star, and ideally to X star that is the optimal solution to the original centralized problem. And if you build the algorithm appropriately, by defining this information vector, Zi that relates to the communication between agents, and the structure of this penalization term, then you can guarantee that it is indeed the case that you converge to the optimal solution of the centralized overall one block problem. In order to converge, you need to iterate and keep exchanging information on your own tentative solution, Xi star Zi to the neighbors, receiving from the other neighbors the same information, and then keep updating and iterating. And in the long run, if you build the algorithm in the appropriate way and subject to appropriate connectivity assumption, you're going to converge to the optimal solution. So what are these ZI and this proxy term G? So in this proximal distributed algorithm, the ZI is just the average of the tentative solutions of a neighbor, including the agent itself, weighted with this alpha ij coefficient, which in order to handle also time-varying communication network is a function of an iteration number k. So if it's 0, it means that agent I and j do not communicate. Agent I doesn't receive any information from agent j. And then the term here, it's added to penalize the disagreement, because if you remove this term, each agent would select the best decision according to its own objective function, which is in general different from the other optimal decision. So you need to weight the difference between agent I local decision and the average of a decision of enabling agents. And the more you weight this term, the more you enforce agreement, because the more you penalize disagreement. So this CK, as we'll see shortly, needs to go to 0 to asymptotically enforce agreement, but not too fast to avoid losing optimality. So what are the conditions? You need convexity and compactness, which I imposed earlier in our database framework. You need this term to go to 0, sum of CK square convergent, but not too fast. The sum is infinity. Think about 1 over k, the harmonic series. And then you need also to appropriately weight the information of the other so that the agents influence each other equally in the long run. And this is stated as a double stochasticity of this A matrix. This is quite technical assumption. And the one that it's easy to explain is you need network connectivity, because you need all agent, the information computed by each agent to reach all the other ones, either directly or indirectly. You can cope with the loss of connectivity in an iteration, but in the long run, any pair of agents should communicate infinitely often with each other with a bounded intercommunication time. And under the structural and nectoral assumption, you can actually prove the convergence of all the tentative solution of all agents to the minimizer of the centralized problem. So getting asymptotic agreement and optimality. So you can use this algorithm, but there are others. There are others based on gradients, subgradient methods. Here are a few that you could use and still preserve the probabilistic robustness guarantee that I showed you before. So there are other works in the literature that address multi-agent uncertain optimization, especially in this case of decision-coupled problem. In particular, the closest one is the one by Lee and Nedich of a few years back. They get stronger result, almost sure convergence, rather than bounding the violation probability, but there is a catch. They need to sample constraints infinitely many times, which doesn't satisfy it's not really a database approach, because it assumes that you have infinite scenarios. So we get weaker guarantees, but with a finite number of samples, and we don't need a tailored scheme for what concerns the distributed computation to preserve privacy in order to provide these guarantees. So here I'm skipping the part. You can similarly, for multi-agent constraint coupled optimization, reduce it to a standard multi-agent constraint coupled problem from which there are a number, I wouldn't say 1,000, but a number of resolution approaches that guarantee convergence to the optimal solution, and so inherit our probabilistic guarantees. Here then, if I'm allowed to share slides, you will see one of them. So concluding, what we consider here in this work is database cooperative optimization over networks, where agents try to solve a constraint, couple, or consensus problem while accounting for uncertainty known from data. And we were able to accompany the agent decision with probabilistic certificate, but all through respectively of P, because P is assumed not to be known, so it depends just on data. So the result is distribution free, as is classical in scenario theory. And we discuss also how decision can be computed in a distributed manner using a general distributed architecture that doesn't require specific tailored distributed algorithm. So what are the open problems? Actually, we started and we are almost there, submitting this paper, providing tighter bounds by avoiding to use subadditivity property, but directly characterizing the violation of the multi-agent system for a given confidence level. We are also trying to address the non-convex case, at least in a structural subcase. And I think the more challenging extension is the one related to removing the data independence assumption, which is key to the scenario theory result. And the fourth aspect is considering more application. I showed just one, but I didn't provide you simulation result because of the time constraints, but there are more where you can apply these results. So this work is a joint effort with Alessandro Falsone and Simone Garatti, associate professor at my same institution, and Costas Margellos, who was a postdoc here and is currently, since a while, associate professor at the University of Oxford, and was partly supported by the European Commission under two projects, one on future artificial intelligence research and the other one related to our Ministry of Education, data-driven cooperative framework for the management of distributed energy and water resources. And so with this, I would like to thank you for your attention. And I'm ready for a question if you have any interest. Okay.
Thank you, Maria. I don't know if you are, you can see me. Okay, I'm here.
Yeah, I can see
Maria.
you.
Thank you again for starting this new year with this very nice and sharp results.
I wish it was clear enough because the timing it's. If you want to say too more, maybe too much, maybe. Okay. So I wish I conveyed the right.
I think we have one question.
Yeah, sure.
Someone raised the hand. I don't know who. Let me see. Mohammed. Please go ahead.
Yeah, thank you so much, Maria. Very interesting talk. So at the beginning that you set up the problem, I saw some dynamic constraints as well. At least that's what I realized or understood. But later, I was wondering if you like embedded those constraints also in that general problem formulation or no?
Yeah, because for example, you have the dynamics of a battery in my example, but it could be a dynamical system that evolves, and the idea is that you unroll the dynamic. So you have this dynamical system, discrete time, for example, dynamical system like in MPC.
Yes, exactly.
It could be that the problem you're solving is an MPC problem, the finite horizon. A finite horizon optimization problem. And if you unroll a dynamic, you make all the variable, the state variable, in that case it was the stored energy, a function of your decision variable, which was how much you put inside. It could be in principle if a disturbance is acting, also a function of a disturbance.
So my question is, could those dynamic constraints also be involved in this model of like modeling? Because all the constraints that I saw was some like inequalities, like gx less than 0. I really didn't see any dynamics.
Yeah, but let's see that you have your, let's do the example of a storage of an integrator. You have the integral of your control action.
Mm-hmm.
And you have to define, like in MPC, the sequence of all the exchanges with the battery, with the storage system. And then given the initial condition, you can compute what's going to be the stored energy given a certain choice of your input. At time 1, and then at time 2, and at time 3, you can make it explicit as a function of your charging and discharging decision variable. And then the constraints on the capacity at every time instant can be written as your decision variable belongs to a certain set.
Okay.
I mean, yeah,
Okay.
the trick is like, it is exactly like if you are familiar with an MPC problem formulation, you unroll the dynamic, either you keep the decision variable additional one, but you make your problem complicated, or you unroll the dynamic as a function of disturbances, your control input, and then you can formulate your optimization problem subject to constraint in this form. So it's exactly, so they become like algebraic constraints. Yeah,
Okay.
set constraints.
Okay, great.
Yeah,
great. Yeah, thank you. Thank you so much.
You're right.
Thank you, Mohammed. Questions? More questions? Of course, you can write the questions in the chat if you want. Daniel, please.
Danny.
So it's very interesting new stuff for me to learn about. I was curious about two things. One of which was, it sounds like these agents are partially cooperating but not fully cooperating. So they're not adversarial, but they're not fully cooperative. Is that the case?
Okay, so they are willing to choose the best solution for the whole system, but actually they are not willing to share their private information. But these distributed schemes are built to this purpose. So when I started working on distributed optimization, my motivation was to address large-scale system, but then I realized that distributed optimization is useful also when it's not large-scale, but you don't want, you don't want to share with the others your private information, which is coded through your cost function and your constraints, but also with data. Let's see also in this new emerging aggregate of prosumers that, offer services to the grid, balancing services, whatever. They are willing to participate, but not to share their personal consumption profile, because otherwise other people know when I'm at home, when I'm not at home, when I use my devices. So the distributed scheme allow to look for the optimal for the overall good of a society, but without disclosing your private information. So it's cooperative. I'm not considering adversarial, but it's a cooperation with privacy.
So if it were to become more adversarial, things are on a scale, would it just mean that the constraints got tighter in terms of what you would share? I mean, each one would scale its own sharing constraints?
You don't share constraint, you share the tentative value of the solution here. In the scheme that I show you, you just share the solution.
Okay.
But I keep my constraints and also my data set. Yeah, this is common also if you look at these federated learning approaches where everybody want to learn using also the other experience, but they don't want to share data.
Yeah.
So we started working also in this framework exactly because the distributed schemes are useful for that. You can preserve your local, you can work for the good of everybody, that everybody can learn more by exploiting the experience of the local ones. But unless you are part of the same company, I mean, you are not willing to share with the other information how your device was working, but maybe the device is the same because you bought it from the same company.
And so the second question was one which, I mean, in the building scenario, it doesn't make a lot of sense, but I have this, thinking of a scenario where cars are passing through communications blackouts, right? So you go through a tunnel, right? And if you want a fully automated car, it can't go crazy when it loses communication with the network. And so is this scheme, if the network goes down or partially goes down, are the individual agents able to operate, still optimized, basically given the old information from the network and their local information? Or is there a scheme to handle that? Right. So I don't know if that question makes sense,
So
but I'm thinking of.
So this is more on the, okay. So this is more on the effectiveness of distributed optimization scheme.
Yeah.
So in a constraint coupled setup, you can end up in situation where, let's say that they get completely disconnected to groups. At the end, each one, you get a suboptimal solution where each one is optimizing a share of a common resource.
Okay.
In the very limit, each one would optimize the use of its share. So let's say that you have a shared, like a shared storage. You could still get a feasible solution if you divide the storage in 1/m part, and each one uses its part. But you can get a better solution if you share the resource, because when needed, you use more, and when not needed, you use less. So for the scheme that I didn't show you, because there was no time, where you do the optimization in the constraint coupled case, you end up, if at some point you get completely disconnected parts, each one optimizes the shared use of a subpart of a common resource, and you still get a feasible solution. For the one where you need to reach consensus, I mean, you need to preserve this connectivity, at least in the long run.
Yeah, so I think the scheme, the car in the tunnel analogy is you temporarily lose connectivity, right? So you have old data from the old shared data and current local data, and then connectivity will be restored. And is there a graceful way to go between those to formulate that so that during the time that I'm disconnected, I'm using my old network, the old data from the group and my local data, and then when I connect back up, it gracefully comes back in. This is probably a very complicated addition to the problem, but I'm here.
I mean, here the algorithm is expected to find the solution, and just when you find the solution, you apply it. So in your example, I don't know if it really meets this perspective, because the idea is that you need to compute a solution before applying it. So you need to reach convergence. There are also algorithms that guarantee finite time convergence in certain setup, like in non-convex setup, or convergence to a feasible solution. But then it's messy with respect to database guarantees, because scenario theory relies on the convergence to the optimal one. So we have been developing other tools that guarantee provide probabilistic guarantees for feasible, not necessarily the optimal solution. But in that case, you get bounds that are very bad, scaled poorly, and then, this epsilon is very high, the violation. So it becomes meaningless. So it's still challenging. There is still a lot to be done. In this respect. You're welcome.
Thank you, Dan. More questions to Maria? Let me check the chat. No.
Yeah, sure.
Maria, I just have some quick questions about, for example, is there any impact when M, the number of the agents, increases largely in the theory? How can we see this? And have you investigated this?
Okay, from the point of view of from what perspective the guarantees? I mean, the guarantees that we provided are all true for every M.
Okay.
But it's okay. Evidently, if you have a constraint coupled problem, the number of decision variable grows with M.
Okay.
So the bounds gets worse.
Okay.
Yeah. So instead, in a consensus problem where the dimensionality of the decision vector keeps the same irrespective of a number of agents, it scales much better.
Perfect. And and the next one is something personal. Have you handle or thinking in handle delays in part of the loop, or there
Sorry,
is
what?
no sense delays about delays
In what loop?
in your optimization
Okay.
optimization process? Yeah.
Okay. So I didn't get the question. Sorry. What's lacing?
Repeat the question. So
Yeah, I
in your-
didn't get the question. Sorry.
okay. Have you considered or there is any possibility to consider delays in the optimization problem? Delays, for example, in the communication between the agents.
Delays. Sorry, I didn't get
Delays,
that. Okay,
yeah.
okay,
Time
okay.
delay, time
So,
delay.
yeah,
Yeah.
time delays. Okay. So these are the algorithm that I show you. It's a synchronous algorithm that assumes that at every iteration they do communicate. So they should wait for each other to get an acknowledge on the reception of the message. But there are other algorithms. So I showed that because it looks to me more simple, but there are algorithms instead that are accounting for package drops or
Okay.
delays. My example was just to show that there are algorithms that works in a distributed way, but you can find the one that I show you is not robust against delays or package drops. It's just robust against the time variability of the networks. So in some sense, you could use or even loss of communication if you interpret the delays. But I mean, it's complicated. It would be a trick to handle them. So there are other algorithms that account directly for them. So the point here was not on the distributed part, but was on the probabilistic guarantee. And once you have an algorithm which is robust again against delays or against a package drop and guarantee convergence to the optimal solution, that solution that you find, you can accompany with the certificate that we derived. So in this respect, we don't depend on the specific algorithm, distributed algorithm. Another dog. Wonderful.
This is
He
a big
usually
one,
joins the
right?
meeting.
Wow.
Yeah, beautiful.
He's supposed to be very
Yeah,
smart.
I don't have
so
mine here because I'm at the office.
I keep him
Next
keep
time.
asking him to check my papers, but he doesn't do it.
Beautiful.
Don't do it.
What the best end of a seminar.
I think we need to, from now on, we need to create some sessions to show our pets. This is the
Yeah, pet
to
sharing.
close the session. Yeah.
Yeah, we bring mine. Yeah, very nice.
So,
I
guys,
didn't-
I don't know if we have more questions. Thanks for the talk. This Andrew is speaking.
Thank you, Andrew.
Okay. So
I can
if
send you the
there are-
slides as well if you are interested, or I don't know.
Yes, please.
That would be
We
great.
can,
Yes.
Okay, so you can
yeah,
post
we
them.
can share this. We can share this with all of them.
Okay.
Yeah.
Okay, very good.
So, guys, if we don't have any other questions, I think.
Thank you,
we-
everybody, also because of the
Thank
time
you,
of the
Maria.
day. That was
Thank you, Tiago.
so now
Thank
you
you,
can
Ben.
have another coffee, Danny.
Yeah.
I'm going for dinner. No, not now. Okay, take care.
So,
It
guys,
was
thank you
great.
again.
Thank you for this opportunity.
Bye,
Thanks
everyone.
to everybody for attending.
Thank you, Maria.
Thank you. Thank you, Maria.
Looking forward
See
meeting
you.
everybody in Busan.
Yeah, sure. For
Indeed,
Sure.
indeed.
I
Bye.
hope to see you in the next month with the continuation of the webinar.
Yeah.
So, and of course in Busan. See
Yeah,
you there.
sure. Okay,
See you
thank
guys.
you.
Thank
Bye.
you.
Bye
Ciao.
bye. Bye.
Everyone.